I want to just say a couple of words before we get to the main event. My name is Eric Adams, and I'm one of 8 members of the Freeman Committee, and we're part of the Boston Society of Civil Engineers section of ASCE, which annually puts on this lecture. And in a couple moments, Peter Richardson from BSCE will say a few words about that organization. This lecture is in honor of John Freeman, who, as many of you know, was a graduate of MIT's Department of Civil Engineering back in the 1870s. He was a world-renowned engineer, both a civil and a mechanical engineer. In the waterfront, he was instrumental in the design of the water supply systems for the city of New York City, San Francisco, and locally he was the designer of the original Charles River Dam. And he gave a gift to Boston Society of Civil Engineers back in 1925, and that fund from that gift has allowed us to put on this annual lecture each year. It also allows us to give small grants to students and to young professionals, both in the private and the public sector, to engage in educational activities. You're welcome to check out our website, which lists all of the projects that have been supported recently. And if any of you are interested in receiving a small grant and you fit the right demographics, please let one of us know. Also, if you are interested in suggesting a topic for a future Freeman lecture, we'd be happy to hear about it. Okay, with that, I'd like to turn it over to Peter Richardson and maybe remind people at the same time, if they've got a cell phone, to please make sure that it's turned off. Thank you.
Thank you, Eric. Good evening, everyone. I'm Peter Richardson. I am the president-elect of the Boston Society of Civil Engineers, and I want to welcome you to the 2012 John R. Freeman Lecture. I want to thank MIT for hosting this event, as they have been doing for a long time, and to the Freeman Committee for putting together another good event, which they've also been doing for a very long time. So just a few brief words about BSCE and some of our upcoming events. For those of you that don't know who the Boston Society of Civil Engineers are, we are the oldest engineering society in the country. We were around 4 years before ASCE. We later became a section of the American Society of Civil Engineers. We hold over 50 events every year. Not all of them are free, unfortunately, like this one. We have 10 technical groups that are very active. We put on technical training. Tomorrow we have a 3-day bridge inspection refresher course. We run a PE refresher course. And then we advocate for infrastructure investment and also for sustainability, and also just for the civil engineering profession in general, for both education and the profession. A lot's been going on with the society the past year. This year we hired a new executive director, Tony Punton, who's a professional engineer. And Tony is actually sat on the board of direction for ASCE. He's been involved at the national level. He's on the report card committee. So he's bringing a whole new dimension to the society with some contacts at the national level and a whole new level of energy. We're very excited about that. Rich Keenan is still staying on as the society manager. So we have somebody who's high up at the policy level now and somebody who's running the events. The BSC recently formed a sustainability committee, and I would encourage anybody who's interested in that to contact the board and see if you can get involved. We hope to support the Institute of Sustainable Infrastructure at kind of the section level. One of the aspects of that, the new ISI, is they have the Zoffness program at Harvard Graduate School of Design has gotten involved, so we have some local contacts there, and we want to support that group at the local level. We've also revamped our website. I would encourage you to check it out, bsces.org. And we've been holding our board meetings this past year at the student chapters. So we kind of taken our board meetings out on the road, and we're trying to establish a better rapport with our student chapters. So I would encourage any MIT students, we'll be coming soon, and we'll have a board meeting with you. This year, the Environmental and Water Resources Technical Group became a chapter of EWRI at the national level. So that's our third technical group now that's an institute chapter. And just so that's some of the things going on. We've been really interested in this talk tonight because we've been promoting resiliency, in taking into account the effects of climate change. So I'm very interested to hear what Dr. Palmer has to say tonight. And just a couple events that are coming up. May 1st, we have our Bertram Berger event, and that's going to be a panel discussion with representatives from FEMA, the Federal Highway Administration, and representatives from all 6 New England states are going to be talking about disaster assistance and mitigation and Hurricane Irene and how they dealt with that. So May 8th, we have Design Professionals Day at the State House. I would encourage anybody who wants to attend that event. It's a great opportunity to talk with your local representative and state senator and advocate for infrastructure investment and the things that are important to the engineering community. On May 9th, we have the Ralph Salvucci online bridge contest, the awards dinner, and at that night, Craig DiLoretto, who's the president-elect of ASC, will be the speaker at that event. So we'd encourage that. And for students, it's a discounted price. So with that, I'd just like to encourage any students here, actually anybody here, to get involved with BSCE, but especially the students at become active in your ASC student chapter. It's a great way to meet people and build the relationships that you're going to need through your career. It's a great way to give back to the profession, and you'll get as much out of it as you put into it. So I would encourage you to do that. And with that, I would just help you enjoy the lecture tonight. Thank you.
Thanks, Peter. This is just like school. There's nothing illegal about the front rows. We promise we won't ask you questions, but you'll be more visible to the speaker if you want to ask him a question. I'd like to now introduce Rich Vogel, who's from Tufts, who will do the real introduction of Rick Palmer.
Evening, welcome, and thanks. Yeah, it is strange. You're all way up there. Okay. Before I introduce him, just want to make one announcement, very brief. I'm from Tufts, and both Tufts and the University of Massachusetts at Amherst are collaborating and sponsoring a symposium this Friday at Tufts. It's actually at Tufts. You can find information on the table where you entered the building, or you can just Google Tufts water and find it online. You're all welcome. It's on valuation of water. Rick Palmer. So Rick has been very involved in the American Society of Civil Engineers. I was thinking, as we just heard, about the Boston section, and that'll come through in the theme in a moment. He received his Bachelor of Science in Civil Engineering and then a Master's from Stanford later on after Lamar's Bachelor's, and then he went to Johns Hopkins and received his PhD in 1979. Some of his work there, just early in his career, was really quite memorable because a portion of his research contributed to a team effort on the part of Johns Hopkins and the Potomac River Basin Commission, which was recognized as a finalist in the ASCE Engineering Achievement of the Year Award. That's normally a bridge or a building or something like that. It's a structure. Well, his team was acknowledged for the improved an evaluation that showed that improved operations of a metropolitan Washington water supply system. So it's a very unique contribution. Currently, he's the department head at the University of Massachusetts at Amherst. He spent most of his academic career prior to that, from '79 to 2008, at the University of Washington in Seattle. Right now, you may not realize this, at UMass Amherst, he's in the systems area, and there are 2 other colleagues of his there. He heads up one of the most vibrant water resource systems group in the country. There are very few universities, you can say, that have 3 experts in that area. His primary expertise is in the application of structured planning approaches to water resources, on things like looking at the impacts of climate change on water, drought planning, real-time operations and management of water resources, and the development of decision support systems. But what is he really known for? Briefly, for introducing the concept of shared vision planning. Look it up, Google it, shared vision planning. It's now accepted, widely used technique by the U.S. Army Corps of Engineers, and it was his invention primarily. the use of virtual drought exercises, and also for many papers on this climate change business. He's been working on the U.S. water resources, impacts of climate change on U.S. water resources, Columbia River, Colorado River, Sacramento River, and on. And now you'll hear about the Connecticut, I'm sure, today. He's got a lot of awards from the ASCE, best papers. He used to be the editor of the Journal of Water Resource Planning and Management as well, but he also received a Huber Award and a Heinz Award. So he's been very involved throughout his career in leadership levels at the American Society of Civil Engineers. Of course, he's also a jazz enthusiast, and he claims that he doesn't play the saxophone very well, but most importantly, I would argue he's a wonderful person, and he gives great lectures, which you're about to hear. Welcome.
So good evening. We'll do a little mic check. Is that volume about right for everybody? Great, terrific. So I'm going to go back a slide and sort of introduce a talk. But first let me say thank you so much to the Boston Society of Civil Engineers for inviting me, and for Rich for providing that introduction. It's a great pleasure and honor to be here tonight. And I do want to note or follow up what Rich said, which is that this is an extremely skewed audience. There must be something in that, what I would consider a northeast corner, that's attracting people, because that's quite a group. Tonight I'm going to be talking about really 3 items, and I'll make those clear in just a moment. I want to say one other thing before I get started too far along. I wanted to say something about connections to MIT. On my faculty at the University of Massachusetts, we have 3 faculty members who received their PhDs from MIT, one from transportation area, one from the geotech area, and one from the environmental area. But my first, I would say, and most meaningful connection to MIT came from my PhD advisor, who was Dr. Jared Cohen, who was at Carnegie Mellon when I got my PhD. Jerry went on from Carnegie Mellon, why am I saying that? Johns Hopkins University. I was recently talking to people at Carnegie Mellon. So at Johns Hopkins, and you'll see why I said Carnegie Mellon, he went to Yale, and then he is now president at Carnegie Mellon University, one of the few civil engineers who have ended up being presidents of major universities. And I guess, when I was a student, as some of you are in this room, and getting my PhD, I thought MIT must be a wonderful place because they produced an individual of such a high quality as Jerry. And so let me just say that anything tonight that I do well certainly can be attributed to Jerry, and faux pas like my mistake in confusing Hopkins and Carnegie Mellon are certainly all my own. So I'll talk about 3 things tonight. I'm going to talk about climate change, and I'm going to talk about it from the point of view of someone who works with people who are excellent climate modelers. And so that's not the same as being a climate modeler, but it's been a role that I've played for a number of years now. I'm going to talk about the impacts of climate change and water resources, and I'm not going to talk about some of the examples that Rich commented on. I'm not going to talk about the West, where climate impacts are going to have really substantial impacts, but I'm actually going to focus on a study we finished a couple weeks ago on the Boston system. But I think the study, even though it's not going to show catastrophic effects in the Northeast of climate change, I think it will be helpful in illustrating how we go about evaluating the impacts of climate change. And I'm going to say a few words about decision making and basically bringing the public and various stakeholders into that process. Like any talk that's done about climate change, we're going to talk about uncertainty, and I think this is a theme that engineers are very comfortable with. They realize that they have to make decisions in the face of uncertainty, but we'll talk about this in some detail. And in general, I would say the theme is how do we sort of rationally plan for a future that's really uncertain. So I wanted to start off with 2 quotes by 2 international leaders. The first one is our President, Barack Obama, and I'll just read this to you. Today we're seeing that climate change is about more than just a few unseasonably mild winters or hot summers. It's about the chain of natural catastrophes and devastating weather patterns that global warming is beginning to set off around the world. He continues with the frequency and intensity of which are breaking records thousands of years old. I think probably a number of you have looked at some of the number of warm temperature records that have been broke recently. And so President Obama was referring to this chain of natural catastrophes. Tony Blair is speaking to slightly a different topic. He says, the blunt truth about politics of climate change is that no country will want to sacrifice its economy in order to meet this challenge, but all economies know that the only sensible long-term way of developing is to do it in a sustainable basis. Two politicians who see the world, I think, correctly, but also are pointing out some of the challenges. I want to say a couple of things. We're going to look at 4 what I would consider iconic representations of climate change. And I think it's good to get people involved. So if you recognize this iconic representation, raise your hand, okay? So how many of you know this graph? Okay. So I apologize. It was said that I wouldn't ask any questions, but I want to ask a question. So what's this graph called? The hockey stick graph. Terrific. And what the hockey stick graph does is the following. It looks back, and it depends on which graph you see how far back it goes, but maybe back to 1,000 years. Deviations in temperature from a standard which is set somewhere right around in here from 1961 to 1990. So what we take from this, I want to add one more thing in this figure. Actually, I can do it from here, is the gray. So what does this gray represent? The gray represents our degree of uncertainty associated with our estimate, our best estimate. And the black line here is a running average, I'm not sure, maybe a decade or so of these numbers. But the gray represents our uncertainty associated with that. Now the gray gets smaller and smaller as we move from ice cores and other types of information out to actually measured thermometer data. But what we see here is a trend, a remarkable trend, and some uncertainty associated with that. So notice the gray in this. We'll talk about uncertainty. In addition, I just wanted to say that at the University of Massachusetts, Amherst, one of the co-authors of the paper, the primary authors were Mann and Bradley, and Michael Mann was a postdoc with Ray Bradley when they developed this. And Ray's a colleague of mine who I work with often. He has a British accent, which, as we all know, raises everyone's IQ by about, 15 or 20 points. And he wrote a really remarkable book, which I would highly recommend. It's a little hard to read, but it's called Global Warming and Political Intimidation. And so if you want a fun read, you might take a look at that. Ray was called into Congress and he was asked to provide all of his computer files for his entire academic career to Congress because some representatives from the state of Texas, my home state, and Oklahoma were uncomfortable with what Ray was saying. So I'll just point out one other thing. We talked about gray. You can notice the gray in Ray also. He has quite a bit of gray. Excellent colleague and excellent researcher. So that was one famous iconic graph. How about this iconic graph? How many of you have seen this graph? Great. Well, we've all seen this graph. There might be a trend in this data, perhaps. We see this going along. And so we're looking at CO2 concentrations over time from the late 50s. I downloaded this data actually and plotted it up so we'd have the most recent data. So it's like up to 2 months ago, I think. We have all the data, and what we see is a very clear trend, seasonally varying, but clear trend for CO2. That's our second iconic figure. Third iconic figure, how many of you have seen a greenhouse gas figure like this? Almost everyone, I'm sure. So very simple, intuitive explanation. In general, the public understands this. It's an explanation for why we have a climate that's habitable rather than being sort of a frozen ice ball flying through space. Greenhouse gases trap the sun's energy, reflect part of it back, and keep our temperature moderate over time. So that's our third image. And then the fourth image I want to present is this one. So how many of you seen this image? Where's it from? Okay, and the IPCC is the Intergovernmental Panel on Climate Change. And so we're going to see quite a bit of data tonight based on that. And whoever answered that, can you say something just about the B1, A1B, and A2? What are those?
Assumptions with the technology and mitigation strategies.
Okay, so let's call those emission scenarios. They're emission scenarios, so they're future estimates of what the CO2 production might be over time based upon a social estimate of what the world will look like over time. And so we all know that there are things we can't forecast in the future, but this is our best guess of CO2 production over time. So if we were to cap CO2 production in today's standards, right now, this would be the estimate of what the global warming would be into the future, still rising over time, but the A2, A1B, and B1 are all projections which are significantly greater and somewhere between 1.5 and 3 degrees Celsius increase in global temperatures, not at any one location, in overall global temperatures by the year 2100. So tonight you're going to see some forecasts associated with 2030, 2050, and 2070, all taken from these emission scenarios. Okay, so those are our four iconic graphs. So I started working in climate change in the early 1990s, and I would say it was a hard slog then when we talked about climate change with people. As it turns out, one of your former speakers in this series, Gene Stockew, who was at the Institute of Water Resources for U.S. Army Corps of Engineers, wanted to look at what the impacts of climate change might be on some of the core installations. And so he brought together a team of people, including researchers at University of Washington, and the primary one was Dennis Lettenmeyer and myself, and we were looking at the impacts of climate change. By 2006, things really changed. I would say the early 2000s, it was hard to get people's attention, so two things occurred right about here. Front page article, Time magazine. What was the other thing that happened? Anybody go to the movies in 2006? So what was that? Yeah, Inconvenient Truth. So in quick succession, in April and May of 2006, two very large media events occurred. And I would say in giving public talks, you could really sense a difference in people's perception of climate change. These two events, and Al Gore had that really famous picture of the graph I put up where he was on a cherry picker that was lifted up as he was showing how rapidly CO2 was increasing. Those things had a huge impact on public perception. So, how many people in this room think that climate change is real? It looks like a lot of people. So I would say, I will tell you, in 2006, in general, that wouldn't have been the response. Okay, we all think it's real. Where's the logical place to look for information about it? Here's a great place. Rush Limbaugh's webpage. Later, I'll talk to you about working with stakeholders, and I can tell you that many of the stakeholders I worked with, this was the place they went to get definitive answers on climate change. And so it's important that we not always go to Rush's Limbaugh's webpage. We might want to go to this thing that we mentioned before, the Intergovernmental Panel on Climate Change. And so this is a few years old. This is promoting the fifth assessment. Tonight we'll be talking about results from the fourth assessment. The fifth assessment will be out hopefully in another year or so. But this is an international group of scientists who produce, I would say, the best vetted science in the world concerning climate change. Excellent reports, and you'll see me quoting from them in fact right now, but also a little bit more later. So in the fourth assessment report, a couple of things were published. And these were the sort of conclusions they came, and this is, believe me, this is the high-level conclusions. There's 3 basic volumes, many other reports associated with this. But at the high level, warming of the climate system is happening. We'll make it simple. It's truly, truly happening. It's evident from observations. It's evident from air temperature and ocean temperatures, the widespread melting of snow and ice, and the rising global average sea level. Okay, there is high agreement and much evidence that with current climate change mitigation policies and related sustainable development practices, global greenhouse gas emissions will continue to grow over the next decades. So it's not stopping yet. And there's higher confidence than in the TAR, that's the 3rd assessment report, in projected patterns of warming and other regional scale features. So when the 4th assessment came out, and the 3rd assessment had been criticized, this was really big news in the sense that 7 years later, there was even more evidence that the climate was changing. The report's broken down in a variety of ways, basic science, mitigation, but part of it is focused on just, let's say, North America. There they talked about the warming of the western mountains. They talked about moderate climate changes that are going to impact agriculture. They talked about the impacts on cities, and particularly on the coastal communities. Massachusetts has a lot of coastal communities, and so Massachusetts is going to be impacted. Let me just show you a couple of examples. This is an example of a coworker of mine when I was at the University of Washington, Phil Mote. And let me just say, this is not a political map. These are not Democrats and Republicans. They're in the state of Washington, Oregon, and Idaho, because that might work. Okay, but let me just show, this is an example of temperatures over time. And what it shows in those locations is that not everywhere, but in the vast majority of cases, there's been an increase in temperatures from 1920, and I believe this was done in 2000, and in some places as much as 3.6 degrees Fahrenheit in those 80 years. And of course, a few places temperatures went down. And this is one of the things I actually learned by working with atmospheric scientists, is that you don't look at one location. You look at many locations. And 3 or 4 states is small in terms of their database. They don't usually work in small areas. And so that's temperature. Precipitation was also up by about 14% in that same area. So there was a general warming in those Pacific Northwest states. But even perhaps more dramatic was a change in snowpack. And so what we see here is a number of locations, as much as 60%, 45%, 30% decrease in snowpack. Snowpack is typically measured at its maximum about April 1st through April 15th in the Pacific Northwest. And the decrease is by as much as 30 to 60%. So all the major cities on the West Coast there, Seattle, Tacoma, Everett, Portland, all get their water supply from mountain ranges in these areas. They're not high mountain ranges that the water supplies come from. They're sort of transitional watersheds where in the spring and late winter and spring, precipitation falls both as snow and as rainfall. Climate change is going to have a really large impact on the quality and magnitude of water that's available. And I've been fortunate enough to do studies actually of all those 4 cities that we talked about, I just mentioned, in terms of looking at the climate impacts. In addition to the total volume, the timing has changed. You can look at studies in the Northeast of freeze out and how that's changing over time into earlier in the year. I wouldn't say that this past winter is a true example of climate change, but it was an unusual winter. Extremely warm. And so let me just point out 2 things that all these things are pointing towards from a probabilistic standpoint. One is a shift in the mean. That is, there's actually less cooler temperatures, warmer temperatures in some locations, more rainfall in some, more less rainfall in others, but basically a shift in the mean over time. And the other issue is illustrated in the middle panel there of increased variability. So I opened this talk, or at least you saw a picture when we started, and we'll see it again, of a flooding event that occurred on the Deerfield River, an enormously large event. And that's a case, I think, of this change in the variability. That flood event had never been seen before, nor was it anywhere in the 100 or 150-year flood event. And so what we're seeing is really shifts in the variability of stream flow over time. So let me, well, that just says that. This is another quick shot from the IPCC about a general framework for looking at the impacts of climate change. And I think the point I want to make here is that there are a number of issues here. One is climate, natural variability, and man-made changes. But at the far end is a question of development. And this feedback loop between where we developed and whether that has an impact on climate change is extremely important. I'll show some more figures of risk in a few minutes, but basically sort of the key issues are vulnerability, exposure to the risk, and the weather and climate events that may occur. So we'll keep this framework in mind as we move ahead. Okay, one final comment on this, the IPCC before I move on, and that is their very careful attempts to use nomenclature consistently. So if you read that report, and I would highly recommend looking at least the policy parts of each of those main volumes. They use terms consistently in terms of very high confidence, and medium confidence. So they actually try to use probabilities in their phrasing of things that are going to occur in the future. And what you saw in moving from the third assessment report to the fourth is basically moving up the scale to being more and more confident that climate was going to have a large impact. Another thing that I want to point out before I show you some models is this notion of cascading uncertainties. And it's true in any kind of long-term modeling that we do. But the notion that I'm trying to represent here is that when we forecast emission scenarios, we know that we won't always be correct in those. But we use those emission scenarios to try to look at what the global carbon cycle response might be. And then we use that to feed into our global climate models and look at the sensitivity, and then into what we might think of as regional climate models, things that are at a smaller scale, and then finally into impacts. So the cascading effects of uncertainty really occur at every stage of this process. And I'm going to show you some graphs that kind of bring that out later in the talk. Okay, so that's a really quick introduction to climate change, and so we'll move on and say a few words about water resources. So what I would say, and let me compliment Rich for all the good work that's being done at Tufts. Those of us who work in water resources and think about this as a systems problem, we really see it as the following, that water resources can provide really essential, important social and economic development potential, and they provide for healthy ecosystems. So what we're looking for is how to best properly manage those systems. And basically water resources provide services, and I'll give you some examples in a second. The challenge, I returned from India about 3 weeks ago, and I guess this was really brought home to me in that trip to India. The planet's population is forecasted to be about 8 billion people by 2030. I think when I was in college, it was 2 billion on the planet. So it's just an amazing level of growth over that time. And our goals in working in water resources is to optimize, to find the best we can do with the available surface and groundwater sources to deal with all these competing needs that we have. So here's just a couple of quick shots. One's, as I said, on the Deerfield River, a flooding event. Let me just say, there's a dam right here. It's probably not serving its purpose in terms of holding back water, best I can tell. It's Southern California. This is just a drought event and a public water supply system that it's much lower than anticipated. I think you can ask the question, so are water resources a big deal? I mean, is there money associated with this? We're civil engineers in general, so we know that it's true. Here's an example of flood damages running from about 1903 to last year. So we have years in which there's $50 billion in flood damages in the U.S. And so it's not usually that high. You know, it bounces oftentimes above the $10 billion amount. But flood damages are extremely important. Droughts, also important, not quite on the same scale. We have some really important droughts. Data back in the 30s where we had some really significant droughts is harder to get good estimates. This data is from the National Drought Mitigation Center, Don Wilhite and his crew there. But what we see is that a number of drought events have been significant, again, in the 10 billion all the way up to about the $60 billion impact level. So how we manage our water can be extremely important. It is all, yes, it is all inflation adjusted. So comment on services provided by water. This is just a shot of the West. What do we do with water? We provide drinking water, we provide navigation, irrigation, environmental flows, or a lot of environmental services and hydropower production. So I'm really going to focus today principally on water supply, but obviously water provides all these other functions. So a couple of quick comments about dealing with uncertainty. You know, civil engineers, water resource engineers are very accustomed to dealing with uncertainty. Here's a shot, that's the Potomac River Basin, little icon up there. This is a place called Point of Rocks, data from 1895 to 2005. If you were, let's say, a chemical engineer, this would drive you crazy, right? If you're a chemical engineer, you're like consistent inputs to whatever process you're working with. Well, this is not consistent inputs to a process. So I would, someone note, what's the first thing you note from this? What draws your attention? What do you think? High flows, low flows?
The big flood.
The flood, exactly. I didn't actually put Rich up to saying that, but that's the first thing that I think people's attention are drawn to. And so this was the Great Flood of 1936. A flood all along the East Coast, had huge damages on the Potomac River. Does anybody else see anything else in that data set that might be of concern? Seasonal variation, yep, seasonal variation. Anything else? Clumping, great, clumping. We won't, I don't think I use the term Hurst coefficient. I might use the term Hurst coefficient in this. Now I don't, I think yes, it is in there in fact. So interesting, so I'm gonna hit this again. Nobody noticed that, huh? So that's the drought of the late 1990s and early 2000s on the Potomac River. It's the lowest drought on record. You don't even notice it, right? I mean, not all of us even saw that was sitting there. So we need to blow that up just a little bit. If I blow that up in size, this is that event, and the years around it are probably fairly normal, but during that 3-year span, we had considerably less water available. DC was put on water use restrictions. It was a tough series of years, and abnormally low, just abnormally low. Okay. So we're used to variability, changes. We're used to dealing with our inflows that we can't always forecast accurately, but it doesn't mean we really like it. So what do we do? In general, what we try to do is do what Rich summarized as sort of structured planning. So if I was going to look at water resources planning and management, I would try to set out a very reasonable guideline on how I would do that. So here's a suggestion. You can read this, but real quickly, I would look at what my problems and opportunities were. You know, I have problems, but I also have opportunities. I'd create an inventory. I'd want to know everything I could about my system. And then I'd forecast the future, and I'd also forecast the status quo. What will happen if I just continue to do what I'm doing? I would look at performance measures like my abilities to supply water, my ability to meet flows for fish, my ability to not have curtailments of water use, issues like that, the amount of hydropower I could produce. I'd look at alternatives. I'd look at the best alternatives. I couldn't probably look at all of them because there was a limit of time. I'd evaluate the alternatives relative to those performance metrics I defined. I'd get the best alternative, I'd try to implement it, and then I'd examine that over time. So I would call that sort of structured planning. Okay, so let's focus on one little piece of this, forecasting the future and the status quo. That should be easy, right? Forecasting the future. I think that's pretty easy. Okay, so another friend came and spoke at the University of Massachusetts recently, Jay Lund, and I'm going to steal, this is an idea that I stole from him. Imagine the uncertainties of moving from Europe to the East Coast, and then from the East Coast to the West Coast. Cartoon says, I thought I was interested in uncertainty, but I'm not so sure. So imagine you started on the East Coast. This is a map of annual precipitation. So we're talking about climate change and things changing a few degrees. So you get in your Conestoga wagon and you start across the country, and what do you see? You see you're going from something like 50 to 60 inches of rainfall a year, something maybe perhaps similar to what you might have seen if you had been in England, to ending up in Utah perhaps, where you might see 5 inches of rain a year, right? So we've had to deal, put this in perspective of climate change, right? We've had to deal with these sort of enormous changes as we move west. And we've developed a whole society and an engineering profession that tries to deal with these challenges. But that's not my point here. We'll move ahead just a little bit. So we've always had uncertainties. And so what we did with, ways we dealt with that, to be honest with you, is sometimes to ignore those uncertainties and do some worst case calculations. Look at the worst case. And so we develop ideas like safe yield and firm yield, and what's the most we can get from a water supply system by looking at the historic record. So there are a group of students here. So how many of you, of the students, safe yield, firm yield, are those terms that you might have seen? One or two? There must be no tough students here, because I'm sure Rich would have said, that's a tough student. Sorry. I'm sure he would have taught these ideas. So let me make the point that we have techniques that have been computerized to look at the maximum amount of water we can withdraw from a system, assuming the past repeats itself. And that's how we've dealt with this in many situations. So at first we thought, well, our ability to plan was just limited by data. We only had 20 years of data, then 40 years of data, then 80 years of data. If we had more data, we could plan better. And we recognize seasonality, we recognize random components, persistence like the Hurst coefficient. But all this time we assumed the processes we were dealing with were stationary. They did not change. The basic statistics did not change over time. And then the droughts of the 60s on the East Coast, which redefined Boston's water supply system, and of the 70s in California, and the 80s in several places throughout the US, really started making us think differently. So we had a paradigm shift, and let me just say about this paradigm shift. A paper appeared in Science a number of years ago, and the title of this paper was Stationarity is Dead, Weather Water Management. And so the folks working on this paper, some of the let me back up, some of the very best in our profession, Dennis Lettmeyer being among them, Bob Hirsch, who I had the pleasure of going to school with, and he was my first employer for a summer job, scared me to death, were involved in this paper. And the issues they raised are the following. They said, why is this idea of stationarity dead? Why is it dying? Well, it died because there's been so much man-made change, anthropogenic change of both the Earth's atmosphere, but also of its landscape. And so if we go in and we develop a region and we change the runoff coefficient, we wouldn't expect the runoffs to be stationary over time. So why call it dead now? We could call it dead some other time. Well, it's really time to make some changes on how we approach this problem. And what's the successor? Well, that's really a challenging problem. What's the successor? If we don't think processes are stationary, how are we going to approach them? And what the authors of this paper said was the following. They said, okay, this is hard, but we really have a history of dealing with these things. And it came from another school down the road, Harvard, at least the Harvard Water Program from the 50s and 60s. And the way you approach that is by using the full toolkit, not just engineering, but economics, operations research, statistics, and looking at risk and benefits. And that's how you're going to get beyond the notion of stationarity. So let me try to summarize that in a slightly different way. there's a need for a more probabilistic approach. Now, I would say currently we don't really know how to do this yet, but it's something that we see we're going to have to address. One of the things we need is a stable institutional platform to make climate predictions. So we have a weather service, right? Do we have a climate service? Do we have an organization that's going to tell us what the climate will look like in the future? So no, we don't have that yet. And the current political climate would suggest we will not have that in the short term. What we'll talk about a little further when I talk about stakeholders is that water managers are really looking for what they call actionable science. So 20 years ago, we could, with confidence in a sense, say, I think this is how much water you need to meet demands. And now we're in a different position. But what managers want to know is how much more data or what other approaches do I have to take to be able to know when to take action? And basically, when should I spend money? So one of my colleagues at the University of Massachusetts, Casey Brown, published an editorial recently called "Is Reliability Dead?" to kind of push this idea further. And the notion is that we can't talk about reliability. We don't have a statistical database now to allow us to do that. So we have to think about adaptive management, not really clear signs of reliability. I'm going to take a very short aside here for a second and ask, well, we're not doing good about predicting stream flows in the future. How can we do, is there anything else we're really good at? I just want to show you this picture. As I said before, I was at the University of Washington for a long time. This is a picture of water demand forecasts for the city of Seattle. You can tell they've done a really good job forecasting. The first figure, so about in the 1960s, there was a forecast made of water demands, and I don't know exactly what we were going to do with water to make those demands come true. But we were going to do a lot of things with water to make those demands come true. A few years later, we got a different forecast, a different forecast, a different forecast, a different forecast. You can see all these, this print's a little small, but basically these forecasts run from 67, 73, 80, with three different forecasts, one in 93, one in 97, 2001, 2003. I worked on the 2007 forecast. It still was too high. Doing everything we could, we still overestimated water demands. And what you might think is that we've done a horrible job with what? What are we missing in the forecast, do you think? How about population? Are we missing, maybe we're missing population? Let's take a look. Whoops, sorry. Population has gone pretty much like everybody expected in that area, up. So those are the number of people served over time. I won't talk about non-revenue water and build consumption, but, well, I will. I guess I will say something. Non-revenue water is water they use but nobody pays for. But basically, the revenue, the water that people pay for was about 120 million gallons per day back in 1975. It's down to about 95 right now, where population has grown by about 30%. So it isn't that we've missed the basic piece of this, people served. What we haven't done well is to recognize the influence of cost-effective, low water use utilities, washing machines, people simply spending less or spending more time trying to be water efficient. And the other thing we haven't had in these models is the fact that people are living in a more urban environment now than anticipated, and simply they don't use outdoor water use the way people had planned a few years back. Okay, so the point of that is that there are many things, social things, we don't plan for very well. Okay, so let me walk through this again. I want to say a general overview, then I'm going to give you a cartoon. So attempts to deal with this death of stationarity. So one thing we could do is take the historic record that we have, stream flow. We have oftentimes a great historic record, and just shift the statistics. And so when I was going to graduate school, again many years ago, stochastic hydrology was a up and coming and active field. And so many people who still work in stochastic hydrology have suggested this as a way to deal with forecasting the impacts of climate change. Well, we can also make direct use of the outputs from global circulation models, and I'm going to show you some results of that. Another approach is to use regional climate models, and so the two figures at the bottom attempt to sort of illustrate the difference between a global model that might try to model the entire atmosphere, and the regional climate models would take output from that global model and then model it at a much more detailed level, one that might actually look at the physical features of the terrain that would impact climate. And then another approach is statistical downscaling. And so I'm going to talk to you about a study in which we use statistical downscaling to look at the impacts of stationarity, the lack of stationarity. Okay. So this is a cartoon I just referred to. And what this cartoon is meant to represent is the general approach that we take to trying to estimate future inflows and impacts of climate change on water supplies. So at the far left figure in the black box is the climate model, and I put it in a black box because it's not something that we as civil engineers tend to work with. We take the outputs from these models. The second step in that cartoon is what I would think of as a downscaling method. And what I mean by that is an approach to taking the global models and making it representative for the basin that you're working in. And this is definitely a talk this topic is worth a talk in itself, but we've worked with Andy Wood and Ed Maurer to look at downscaling techniques on the West Coast to make use of that. On the far right side is a schematic of what I would think of as a fully distributed hydrology model. So again, when I was at Stanford in my youth, we used the very first computers to look at hydrology models that were fairly simple in nature. Today, hydrology models are fully distributed. The models that I'll describe today work on a 100-meter by 100-meter grid with multiple layers of terrain, soil type, vegetation, leaf index, very complicated models. And from those hydrology models, we typically put them in that fourth panel, some sort of operations model, and then we try to come up with the final panel, which is some measure of a result that people care about. Okay, so we'll talk about some of these things in particular. So that just explains that. I just wanted to show this. I want to show this one picture, one very simplified picture before I go into the study. This is an example of impacts of climate change on a water supply in the Pacific Northwest. It characterizes many of the things that we see often. So if you look at the blue line, that's a historic runoff from a water supply into a water supply system. This happens to be for the city of Everett. But what you see here is a double hump hydrograph. So October, November, December, this is the rainy season. It gets cold, it rains even more, and if you've lived in the Pacific Northwest, you can only imagine what even more means. And so, but what's happening is that precipitation is coming down as snow, so it doesn't run off, and then in the spring you get a bump when it starts to run off, and then what you see is a very dry May, June, July, and August typically. And really this is just base flow and snow melt coming off, and then you repeat the process. With these what you see here are three different climate models, Eckham, GISS, and IPSL. They're just three of the climate models. And the average of those has much more runoff in the winter because it's warmer and rain is falling, or precipitation is falling as rain, and much less in this very important period. Fish migration, lots of ecological functions that would occur during this period if it was more natural. Okay, so I'm going to talk now a little bit about the Boston area since this is where I am. You all know that the Quabbin and the Wachusett are the two watersheds that provide most of the water. Actually, here That's a great.
Black swans, or do you take it all the way there and say, we've looked at, the actual implications?
Yeah, so the question is, how far do we take this? And so let me say, the study that I was just describing as part of a master's thesis, and so what we did is we put triggers on water use when the reservoir got, and I didn't show any of this, but we put triggers on water supply. So rather than running out of water, you'd have to cut back on water use. So it's easy to do these things. It's just a model, and you put the triggers in and you run them, and so we talked about the vulnerability of the water supply. So those things are easy. I didn't talk about, looking at ecological impacts tonight very much, and so we did a study in the Pacific Northwest looking at the impacts of hydropower production on fish. Really complicated, right? Salmon live only a portion of their life in these streams. They live a large portion of their life in the ocean. So just like the climate models have huge uncertainties, a lot of these life cycles for fish have huge uncertainties. And so really, really challenging problem. And our new Climate Science Center is going to be looking at that. So maybe one final question. Yeah.
I had a question. Another big use or big consumption is industrial.
Yes.
Use, like and bottling beverage companies along with power generation. So
Right.
how would you? So people don't realize that unintended consumption in making the beverage as well as they drink it like it's not water or something else.
Right.
They'd be better off not drinking it at all. But so would you drive up? Would that be a better thing to drive up the price of things like that?
Yeah,
As
so-
opposed to water, directly water consumption.
So the question is sort of the industrial side of this. What about pricing water for industry and what happens with that? So again, I'll use an example from the Pacific Northwest. In the Pacific Northwest, there was a lot of pulp and paper mill work. And so when water prices went up, the amount of recycling of water increased tremendously at those facilities. They were very responsive to water prices. And I think that can be true. The question was raised about, maybe using drinking water for the beveraged, the bottled water and issues like that. I think certainly on the East Coast in most places, that's not a major problem. But if you go to some developing countries, where the Coca-Cola plants take out a tremendous amount of water from a small location and then distribute it nationally, there can be really large local impacts of that. Yeah. So I actually now see there's a clock in this room. It's 8:33, and I think I've certainly used all the attention that I deserve from your time. So thank you again so much for coming. I'm very happy to be here at MIT.